Okay, so last time we left off with the twin paradox. Um, I do want to go back a little bit to general relativity because if you remember last time we mentioned that the person who is in the box, remember we said that uh, the equivalence principle says that if you're in a box, you couldn't tell the difference between you being in a gravitational field or something pulling the object, the box, with a force, maybe some magical being that has a rope attached to the box. I mean, these two would feel the same. Whether you feel you being pressed against the floor due to gravity, or whether you're being pressed against the floor because something is accelerating you upwards, they would feel the same. And there really isn't an experiment that you could do to determine the difference between the two things. So if we were to, for example, shine a light, the person in the elevator would see the light travel in a straight line. They wouldn't see it curve, because if they saw a curve, then they would know that the elevator is accelerating up. So they wouldn't see that. However, the person who is outside would see the light curve because they would see the elevator is actually accelerating up. So the reason why I want to go back to this for a second is because there is actually an interesting thing that happens in gravitational fields. I think you might have seen, have you seen the movie Interstellar?
Yeah.
Yeah. Do you remember what happened when they landed on, I believe it was a planet that had a really, 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 really crazy strong gravitational field? And then they were on the planet for a little bit of time, and then they went back to the spaceship. Do you remember what happened?
Oh yeah, it was like years had gone by, but they were only on that planet for like a few minutes or something, no?
Yeah, exactly. So here's the idea. Remember, the speed of light has to remain constant, right? So the observer in the elevator and the observer outside the elevator, if they were going to measure the speed of light, it would still be c. The difference is this. The difference is the person who's outside the elevator is going to see the light is traveling a longer distance. So if the speed is going to be the same, if c is constant, then the only way that they could measure c to still be c is if the distance is greater. That would mean the time would be greater too, right? Because if the distance is greater, if this represents a greater distance, then the only way to keep c constant is if t would be greater too. What does that mean? That means the person who's observing somebody else in that gravitational field would see that their clock is also taking longer. In other words, it's like observing the moving clock, right? What we see is it's not taken at the same rate. The person who is observing something that's moving will say more time has passed by. So in the movie Interstellar, yeah, they're on this gravitational, very, very strong gravitational field by, I think it was some planet that was near a black hole, if I remember correctly. And because they're in that gravitational field, the time just ticks at a much slower rate. Now, this is interesting because actually this is something that GPS has to account for. Because the satellites are further up, they experience a slightly different effect from gravity because they're further away from the center of the Earth. So the clocks in the satellites actually do tick at a slightly different rate. And that's important because if you're trying to predict locations, you need to be accurate with your time. Otherwise, when you provide locations, if times are off, then the distances will be off too. So that's a really, really interesting phenomenon that time does tick at a slower rate in stronger gravitational fields, or we could say ticks at a faster rate in weaker gravitational fields. Anyways, I just, because I did want to tie it a little bit back to general relativity. Okay, So time dilation is something that comes out of SR. Here's another thing that comes out of SR, which I really like. This one is one of my favorites. It's called simultaneity. All right. Do you know what it means if something is simultaneous? Does anyone want
It
to?
happens at the same time.
Yeah, exactly. Happens at the same time. So let me paint a picture for you. Imagine this. Imagine we have. This is not my own thought experiment. This is, I think, something that Einstein first came up with. Imagine that there's a train. Okay, so there's a train, and there's an observer. First off, can you girls see my screen? I'm assuming you can. Did I ask you if you
Yeah.
can?
Yeah,
Okay.
we can see
All right.
it.
Good. All right, imagine this. Imagine that a person is watching a train that is moving. Let's say it's moving this way. Okay. Now, imagine that there is a simultaneous lightning strike. This is a thought experiment because you would never see this. But anyways, imagine there's a simultaneous lightning strike on either ends of the train. Okay, like that. All right. Now, the person that is stationary would then observe that each lightning strike would then reach them at the same time, right? So they would experience the lightning strikes to be simultaneous if they were indeed simultaneous. If these two lightning bolts hit the front, we'll call this the front end, and the rear end at the same time, then the light would travel to this stationary observer. I'm going to assume that they're stationary at the same time. So this person would conclude that this is stationary. Sorry, stationary, simultaneous. That's what I meant to say. I very don't speak good English. All right, so they would conclude, oh, the lightning strikes were simultaneous. Now, consider an observer in the train. So a person that's in the train also notices the lightning strike. Okay. Now, again, you would need to be going pretty fast for you to be able to experience what I'm about to describe. Okay. Now, lightning hits both ends of the train, right? Now, the light then is going to travel to the observer. So the light from the front end will travel to the observer, and the light from the rear end will travel to the observer. But here's the thing. Because the train is moving forwards, which would the observer notice first? Lightning strike A or lightning strike B? We got something in the chat. A. Yeah. Is that Mahia? Yeah. They would notice A first. And that's because the train is moving towards the front end, right? Where that front end was hit. So the train is moving in that direction. So here's what they would say. They would conclude that the lightning strikes were not simultaneous. So the person at station would say, no, no, no. The lightning hit the front and the back end of the train at the same time. Person in the train that's moving would say, no, they didn't hit at the same time. The front end hit first, and then the back end hit second. So here's the question. Who is right? Anyone want to guess? Who's right? Yeah. Who's that? Maya? I can't see the name. Okay, it is. Yeah, they're both right. They are both right. Now you're like, how can they both be right? Well, because in their own reference frame, what they are seeing is different than what the other person is seeing. So they're both right. The person who's stationary is seeing that it's simultaneous. The person who is not stationary, who's in the train that's moving, would notice that it's not simultaneous. Now think about that for a second, right? So people can disagree on things and both be right. That's crazy, right? So this is, again, where special relativity starts to make your head hurt a little bit. So I want to show you So that's another thing that comes out of special relativity is observers might not agree. They could disagree on events. Now, we're actually going to come back to that in a little bit, okay? Because now I want to actually show you kind of like another thing that comes out of special relativity, which is lengths actually change. All right. Now, let me, before I explain that, I'm going to actually go back a little bit to time dilation. Okay. So here's the idea. A muon is a particle that's created in the upper atmosphere. It's one of the, if you look at the standard model, it actually comes up. Maybe I should actually call it up so you can actually see where it is in the standard model. Hold on, let me. You guys know what the standard model is? You ever heard of it? Standard model of particle physics. Just a way to describe matter. Standard model of particle physics. So let's see if we can find a nice something in the chat. Yeah, we did do it in chemistry. That's right. I forgot about that. Okay, so here it is right here. So let me click on that so we can see it. Yeah, so this might be familiar to you. Make this a little bit bigger. Okay, so here is the standard model. These are the things that make up matter, but also explain force. So the muon is, you could see it right here, right there. There's the muon. Now, it's got the same charge as an electron, but it's a lot heavier than an electron. So I'm not sure if you can see this. Let me make this a little bit bigger. These are the masses of the particles. You'll notice the unit is actually very, very bizarre. The reason for that actually has something to do with the movie you watched. Well, at least I think you watched it. The movie was called E equals mc squared, right? So the mass for these particles are actually expressed as energy per c squared. That's why you'll notice it's per c squared. And the energy is actually in something called electron volts. So we will actually address that in the unit on quantum mechanics. So that's, I mean, you don't need to know that for this. I'm just showing you that the muon, you can see it's about 106 mega electron volts, where the electron itself is like half a mega electron volt. So a muon is like an electron. It's negatively charged, but it's just a lot heavier than one. Anyways, these particles, they're created in the upper atmosphere, okay? So created by radiation striking particles in the upper atmosphere that eventually produces these things called muons, but they don't last very long, okay? They have a half-life of about 2 microseconds. I'm rounding it off a little bit, but it's about 2 microseconds. Now, I got this from, so it's not my own. I came across this, watching a video on from something called 60 Symbols. You girls ever heard of 60 Symbols? Anybody ever heard of this video YouTube channel called 60 Symbols? Fantastic. I love it. It's great. And they have really good explanations. And they came across this one. I gotta talk about this one with my kids. So this is what happens to muons. They're created up in the atmosphere about 50 kilometers up. Now, if you look up the speed of a muon, it's about 99% the speed of light. So they're going really, 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 really fast. Now, what we could do, we could actually work out how long it would take the muons to get to the surface of the Earth. Very easy, right? We could say the time it takes for the muon to get to the surface of the Earth would be where it's created, about 50 kilometers up. So the distance over the speed at which it's going to travel, right? Now, the speed at which it's going to travel is 99% the speed of light. So we could say 0.99 times the speed of light, which is about 300,000 kilometers per second, okay? So if we do that, let's see. Let's work this out. So well, 50 divided by, I mean, okay, so let's say 50 divided by 0.99 times 300,000.
Sir,
Yo.
don't you have to multiply like to get meters?
No, because their unit is the same. It's kilometers and kilometers. Yeah.
But isn't, oh, okay, sorry, I didn't see you.
No swearing. This is PG,
I
please.
didn't say anything.
I'm the only one who was allowed to swear on these things. You know that. Because I can edit them.
Okay, I'm sorry, I didn't see you converted speed of light. I'm sorry.
That's okay. Oh, now hold on. Let me, what happened to my calculation? Okay, 50 divided by 0.99 times 300,000 kilometers per second. So it's about, I'm going to round it up to about 1.7 times 10 to the negative 4 seconds, okay? So that, oops, that's the wrong thing. So 1.7 times 10 to the minus 4 seconds, okay? That's a very, I mean, blink of an eye, right? Now, the thing about these muons, though, is their half-life is only 2 microseconds. So what we could do is we could actually work out what percentage or proportion of muons would be detected on Earth. All right, very easy. So those of you who took biology, remember the formula for population growth times, remember that it's the population times the growth rate over time to the power of t. Now, the half-life equation is actually the same equation. So what we could do is we could say, look, let's start with 100 muons to represent 100%, okay, of muons. The growth rate, because it's a half-life, the growth rate would be 0.5. That means that every half-life time that passes by, half of the particles disappear. They decay into something else. So lambda would be 0.5. The equation for half-life is actually the time over the half-life time, T over TH. Okay, now I'm going to show you something which is really interesting. So if we plug it in, we have a time of about 1.7 times 10 to the minus 4 seconds. Okay, that's T over the half-life time, which is 2 times 10 to the minus 6. Now, if we just do those, let's just do this part separately, okay? Just so you kind of see that. So what is it? What's it? 1.7 to the power of 4, negative 4, sorry. So 1.7 times 10 to the negative 4 divided by 2 times 10 to the minus 6 is about 85 half-lives, okay? So that means that this number, so if I move it over here, let's change the color, make it nicer. Let's see, would be 100 times 0.5 to the power of approximately 85, okay? Now, if we do that, this is what you get. All right, so 100 times 0.5 to the power of 85 would be this. Oh my Lord, that's a tiny number. That's 2.6 times 10 to the minus 24. Okay? 2.6 times 10 to the minus 24. Now that's a ridiculously small number. In other words, you probably never going to detect muons at the surface of the Earth. But here's the thing. Scientists detect lots of muons at the surface of the Earth. So how does this happen? Okay, who wants to guess? Obviously, it has something to do with the title. Muons, time dilation and length contraction. So what is going on? Think about last time when we talked about. Anyone want to guess? So remember we said that the person who is watching the moving clock will see that the moving clock is ticking at a slower rate, right? But that also means that biologically speaking, the moving object's biological clock would be ticking at a slower rate. I guess in this case, instead of saying a biological clock, we could say its half-life clock would be ticking at a slower rate. So what does that mean? That means its half-life would be much longer than 2 times 10 to the minus 6. So the reason why we can detect them at the surface of the Earth is because we'll call them their biological clocks. So they're not living things, but what we're going to call them. They're aging at a much slower rate. In other words, they don't decay as fast because of time dilation. So this actually relates to what we talked about last time. But here's the thing. Because if we go back to the 2 points about special relativity, the first is that, remember, the second point was speed of light is constant, but the first point was the principle of relativity. So, if I'm stationary and I'm watching a moving clock, to me, it would look like it's ticking at a slower rate. But then you could say, well, hold on. If I'm the person moving and I'm watching you, to me, I'm the one that looks like I'm stationary. So you would be the one that's moving. So your clock is moving slower. Okay, so why am I saying this? Well, let's think of it from the point of view of the muon. All right, from the point of view of the muon. Imagine you're the muon, okay? You're this little subatomic particle. Now, from what you see, so here's the Earth, right? You're created up here. You see the Earth below you, right? Imagine you had eyes. Now, for you, it would look like the Earth is doing the moving, right? It would look like the Earth is rushing towards you. So your biological clock would be unaffected because it's not you that's doing the moving. Relatively speaking, it's the Earth that's moving towards you. But if we can detect them on the surface of the Earth, then how do we explain that from the muon's point of view? All right. Obviously, it can't be then something to do with time. It actually has something to do with length contraction. So what else comes out of special relativity is that things moving in a particular direction will actually contract in that direction of motion. So what does that mean? Okay, so let's imagine this. Imagine that you have someone watching a train approaching. Okay, so imagine there's a train that is, I can't draw anymore. What happened here? So imagine there's a train approaching. There's a reason why I want to draw like a three-dimensional structure here. Okay, so imagine a train that is approaching. Okay, like this. So we can see the 3 dimensions of the train. Oh, that looks really bad. Okay, we can see its width. We could see its height. We can also see its length. So that's its length. Okay, so imagine the train is moving like this towards the observer. Now, what the observer notices, the stationary observer would notice the moving object to be length contracted in the direction of motion. So the train might actually look like this to them. Shorter. What's interesting is the width, because the width is, we could say, perpendicular to the direction of motion, and the height, which is also perpendicular to the direction of motion, will be unaffected. But the length, which is in the direction of motion, would be contracted. It's interesting. So from the muon's point of view, the Earth, the distance between it and the Earth would be, that would be contracted. Now, everything, so imagine it was looking at a tree coming towards it, or a building, then the buildings, the distance, between it and the building would be contracted, although all the other dimensions would be normal. I wouldn't even be able to visualize what that looks like. Like, that would make my head hurt, being able to visualize something like that. Now, so that's just another way to explain why we can detect muons at the surface of the Earth, because their distance is actually not 50 kilometers. If it's length contracted, their distance would be a lot less than that. So even though their half-life is still relatively short, the distance they have to travel is just a lot less. Both explanations work, right? They both explain why you're going to see lots of muons at the surface. I say the surface, I think they're actually detected a little bit below the surface. I can't really remember, to be honest with you, but in either case, they're detectable, whether it's at the surface of the Earth or slightly below. By the way, this is the equation for length contraction. So this is what's called the proper length. This is the length at rest. So this would be like the apparent length. So if you were like watching a moving object, you would see it contracted. Now, if we, for example, say, let's say, imagine you're watching an object traveling at the speed of light, then what would its length be? It would actually be 0. Because if it's traveling at the speed of light, that means that this would be c. So that'll be 1 minus 1. So if you were traveling at the speed of light, this would suggest that the universe, the length would all come down to a single point. Everything, lengthwise, width would be the same, height would be the same, everything would be contracted down to, and again, I wouldn't even be able to visualize what that looks like. I have no idea what that would look like. But the next thought experiment, I can actually visualize. This one is actually kind of easy to visualize. And this has to do with length contraction. But we're going to talk about a paradox again, okay? Paradox. That doesn't mean 2 doctors. That was a joke. You don't like it, okay. All right. So the idea with length contraction is an object that's moving relative to an observer will appear length contracted in the direction of motion, right? So imagine this scenario. This is a really cool one. Train at rest, okay? Tunnel at rest. Let's say the train is 60 meters. So let's say the train is at rest, tunnel's at rest. What's longer? Obviously the train, right? So here's my question. Would the train fit in the tunnel? So first glance, you would say, no, can't fit in the tunnel. The train's longer than the tunnel. It's not going to work out, right? It won't work. But what if we were moving at relativistic speeds? Okay, so imagine this. Imagine that you're in the tunnel, or you're watching the train as it approaches the tunnel, okay? Now, what would you see? Well, if the train is moving really, really fast, you would see that its length would be contracted. It would be shorter in that direction of motion. Now, here the example is 36 meters. So, okay. So from the person in the tunnel, from their reference frame, you would say, yeah, that train is short enough to fit in the tunnel. Okay, all right, yeah, so they would say, yeah. Now, however, what if I'm on the train? Now, if I'm on a train, to me, it looks like the tunnel's moving, right? I mean, I'm on the train, we're moving at a constant rate. Remember, moving at a constant rate and being stationary are equivalent. So I can get up from my seat, I can go to the washroom, I can come back. It feels normal, right? I don't feel any different unless the train starts accelerating. Now, I look at the tunnel. I see a tunnel up ahead. To me, it looks like the tunnel is the one moving towards me. So what would I see? Well, I would see the tunnel, or the depth of the tunnel, right, in that direction of motion, would be length contracted. So I would say, no, this train ain't gonna fit in the tunnel. Okay, so now we have one observer who's in the tunnel says, yes, it will fit. The observer on the train says, no, won't fit. Okay, so who's right? Anyone want to guess who's right? Okay, let's add something to this. Now, again, I got this from 60 Symbols, so it's not my own. What if we could force the issue? And this is what I mean by that. In the video, they talk about guillotines. Okay, imagine a guillotine that is on either end of the tunnel, and the guillotine goes up and down. Okay, let me show you the video clip from 60 Symbols, so you can really see what I'm talking about here. Okay, so this is what we were talking about. So that's if the tunnel is shorter than if the train is shorter than the tunnel, right? Either the train is going to be intact, it's not going to be destroyed because it's small enough to fit into the tunnel. So the guillotines will come down and up and the train's okay. But if the train is too big, the train's going to get damaged. So either the train is damaged or it's not damaged. I mean, you can't like exactly argue that point, right? So what's going on? Who's right? Okay, Maya, go ahead, say it.
Can you hear me?
Yeah, I can hear you. Can you girls hear her?
Yeah.
Okay, go ahead.
I think they won't come out at the same time for the other frame of reference. So the front one will come down first, and then once the train passes, the back one comes down.
Beautiful. Yeah, it's actually the same. So the way you resolve this paradox would be going back to discussing simultaneity, where one observer will think the guillotines are coming down simultaneous, but the other observer says, no, they didn't come down simultaneous. So in both cases, the train's not damaged, but the explanation as to why is different, right? So yeah, thank you. Very good, Maya. Very good. I mean, it is interesting to make these observations, to think about things moving at relativistic speeds, to see like some really, really bizarre effects. I think maybe, yeah, we can just mention one more. I'm not gonna do we're not gonna do any calculations. We'll do calculations when we meet up next time, okay? But I want to show you one more thing that actually happens with special relativity. And this actually comes up in the video. In the video, do you remember what happened when the explanation was, or the description of a moving train where you can pump in, I don't know if they use the word infinite amount of energy to make it go faster and faster and faster. But because you can't go faster than the speed of light, you can't really violate the law of conservation of energy. So if you keep pumping energy into the train and it can't go any faster, where does that energy go? You remember that from the video clip? Yeah, it becomes heavier. Very good, thank you. It goes into the mass. So mass increases from when an object is moving at relativistic speeds. Mass actually increases. So we can do like a kind of like a thought experiment to prove this, right? Going back to momentum. Number in collisions, momentum is conserved. So imagine I have an object. Now, normally we do it in meters per second, but it doesn't really matter, okay? Two objects approaching each other at 60 kilometers per hour, right? So, you know, we talked about collisions. That would really be no different than an object that is stationary. So I'm my pen here. Okay, hold on. Let's fix my pen. That would be no different than an object that is stationary with another object moving towards it at 120 kilometers per hour, right? It would really be no different. The same thing. We can think of them as the same thing. They're equivalents. So, you know, in both cases, the momentum would be conserved, right? I mean, in this case here, maybe they will come to a dead stop, cancel each other. Because right now, assuming that the two masses M1 and M2 are the same, then we could say, you know, the momentum cancels out, is actually zero initially. They come to a dead stop, so it's still zero. Or another way we can think of it is, well, maybe, you know, object is stationary, the other object moving towards it at 120 kilometers per hour. That would really be the same as they stick together and they move at 60 kilometers per hour, in this case, to the right, okay? I mean, in both cases, the momentum is conserved. Here's the thing, though. What if we looked at it as 60% the speed of light? Imagine two objects are approaching each other at 60% the speed of light. Well, then you can't really say that it would be the same as the stationary object watching the other object approach at 1.2 c. That doesn't make any sense at all, because that would be greater than the speed of light. So how do you keep the momentum conserved in this case? Because the momentum has to be conserved? Oh, it's easy. The mass increases. That would be the reason why the momentum is conserved. So another thing that emerges from special relativity. So we talked about time dilation, how time is experienced differently, length contractions, simultaneous events, and now lastly, mass increasing as objects start traveling really, really fast. Okay? All right. Ooh, that's a lot. Let me stop recording and take questions.